Alrighty, now we're coming back to pneumatic power. So, previous when we talked about pneumatics and hydraulics and the differences, now we're going to talk about the math of it. So, first off, we got to talk about pneumatic power. Pneumatic power, or first, we're going to talk about pneumatic versus hydraulic, early pneumatic uses, properties of gases. Then we're going to talk about certain laws called Pascal's law, the perfect gas law, Boyle's law, Charles' law, Gay-Lussac's law, and then common pneumatic system components and compressor types and future pneumatic possibilities. So, first off, pneumatics. Pneumatics is pneumo means gas. So we're talking about using gas or air or some form of a gas like that to compress it and use that for powering something. So it's kind of like a spring. You can think of the gas as a spring. Now, gases use compressed gas. They possess a quicker and jumpier motion, are not as precise and require lubrication, are generally cleaner, and often operate at pressures around 100 psi. Generally, they produce less power. Now, hydraulics, on the other hand, are going to be the opposite. They're going to use liquids, and they are going to be very much smoother in motion. They are going to be much more precise. They do not require lubrication because they already have the oil in it, but they are messier because they have oil. Often they will be operating at several psi, several times higher than pneumatic systems, and they are also extremely much more powerful. So early uses, I mean, it was just a simple nozzle when we had blowers trying to use them for smelting. We had different pictures of different systems way back when. They could created a hemisphere where he evacuated the air and used and the atmospheric pressure couldn't be pulled apart by two horses. The first subway system was actually designed to actually be hydraulically powered, and air would be high pressure behind it, pushing the entire system. It wasn't very practical, but it was the first one. Now, let's go to the properties of gases. Gases can be affected by three things: temperature, pressure, or volume. Gases have no defined volume. Gases can be highly compressed, so you can shove them into a small area, and gases are lighter than liquids. So, let's talk about absolute pressure. Now, when you put a gauge on the tire and it reads 30 psi, that is 30 psi plus atmospheric pressure. So you need to add in atmospheric pressure because it's not taking into account what atmosphere is. And so you always want to take the gauge plus the atmospheric is going to get you what we call absolute pressure. Absolute pressure in the United States is equal to 14 pounds per square inch. So if a gauge reads 120 psi, the absolute pressure would be 120 plus 14.7, which it gives you 134.7 pounds per square inch. Same thing with temperature. Temperature does not, or 0 degrees Fahrenheit does not actually represent a true zero. So you need to actually use an absolute scale. So in Fahrenheit, that is negative 460 degrees. In Celsius, we call that the Kelvin cell, or 0 Kelvin, or 273 degrees, negative 273 degrees Celsius. The absolute scale in the Fahrenheit scale is the Rankine. In the Celsius scale, it's called the Kelvin. Unfortunately, you are engineers, so you'll have to use the American standard, so that's the Rankine system. So you just take the Fahrenheit number plus 460, and that will give you your Rankine scale. Now, if you look here, you take 65 degrees Fahrenheit. What's the absolute temperature? That's right, 65 plus 460, or 525. Pascal's law. This deals with that pressure is equal to force over area. So you just take that formula. If you know the pressure, if you know the force, and you know the area, you can get your pressure. So how much? Force, 50 pounds, diameter 3 inches. Now you have to take that 3 inches and turn that into an area. So you have to use pi r squared because it is a circle. So pi to 1.5 squared gives you an area of 1.7. Put those in, 50 over 7.5 gives you 7, a pressure of 7 psi. Now, Boyle's law, Charles' law, and Gay-Lussac's. So Boyle's law says this, that volume and pressure are inversely proportional to each other. As volume goes up, pressure goes down. As volume increases or decreases, pressure goes up. So you can use this equation. The pressure of the beginning times the volume is equal to the pressure afterwards and the volume afterwards. Boyle's law deals with pressure and volume. So there's a good formula. Pause it, look it over. All right, Charles' law. Charles' law says that volume and temperature are proportional to each other. As volume goes up, so does temperature. So, as you heat something up, it's going to get bigger. If you cool it off, it's going to get colder. So this one deals with the fact that heat causes things to expand. So, pause here, look it over. All right, so here's another example of Charles' law. Pause this. Now we're going to go to Gay-Lussac's. Gay-Lussac's, he said that pressure and temperature are also inversely proportional. As you increase heat, the pressure goes up if you have a rigid body and you don't let the volume change. So again, you can look it over, pause here, look at this. Remember that you need to have it in absolute pressures. So here's another problem. Okay, so common pneumatic systems, you can see here you got a pump which goes into a storage tank, then it can go off to its various different components where they can be used for the different systems. So you got your receiver tank, your transmission lines, and your compressor, eventually your cylinders, your fittings, your regulators, your drains, directional control valves, your pressure relief valves. So here's some these are types of motors that actually do compression. So what is the possibilities maybe on the horizon for pneumatics? Could humans transport in them? I don't know. Maybe some future student will build one. So that is it. If you have any questions, ask your teacher.